In this video, we're going to go ahead and kind of delve into a set of data and try to run some simple regression analyses on it. And I'm going to try to elicit or try to exhibit a lot of the different features of the different regression techniques we've talked about. We'll start from a very small, simple regression model, simple linear regression model, and build it up with a few more examples. Now, we're not going to hit everything possible. There's actually more with this data set that we can do. But I want to kind of give this to you as a chance to just see kind of a few of the techniques, go through the actual mechanics of an actual problem. So for this, we're actually going to look at a data set that contains home prices from Albuquerque, New Mexico. And actually, while I'm here, I'm going to pull up a little bit of information about this data set. Let me actually find it here. So the housing prices in Albuquerque, we have this random sample of 111 records of resales and homes from February 15th to April 30th, 93. So it's a little older data set. You'll find that in regression, home prices is a very common first example. And we're basically just trying to say we're going to try to predict the price of the house based on some features. So in this data set, we have price, the square footage of the house, the age of the house, the number of features. Now the features, anything they distinguish as a feature would be dishwasher, refrigerator, microwave, garbage disposal, and so forth. Where is it located? Is it in the northeast sector or not? Is it on a corner or not? And also, what are the annual taxes in dollars? So that's kind of an overview of the data set. And here's how you're going to load it in. If you run this albhome is read_CSV, I have a link here that you can copy off of this video and load it yourself. And also I have a few libraries and a package to install. Now this is not required at all, but this ggalley package, I just found it, kind of links up with ggplot2 to help us try to visualize a lot of these relationships in a fairly quick fashion. So I would recommend that you install it and load it just for purposes of today. So now we always say that the first thing we want to do is kind of look at the relationships. And actually, we could just use the base R plotting. I could just say plot albhome, and I get this big matrix scatter plot. And I can see some relationships here. Like, for example, with price, it looks like square footage is pretty related. I see a pretty strong linear relationship. Age doesn't seem to show much. Look at where age and price come together. Features, well, it kind of seems like the more features you have, you get a little bit more money, but it's little, not necessarily as definitive. Stuff about the corner and customer, corner, northeast, and I actually don't even know what this cust is here, so we're not going to ignore that. Tough to tell. We'll talk about these type of variables next week. And then finally we can look at the tax, and we see the tax is very clearly increasing with the price, which would be expected. Now, I'm going to also, this would probably be the way I look at it first, if you want to use this ggpairs, which is in the ggalley package. It's a little bit of a fancier graph, and it actually takes a little bit of time to do it. It makes a lot more plots. It actually gives you correlation values, so it certainly looks a little bit prettier, but honestly the plot will probably be good enough for our cases just to do a quick view of what the data looks like. And I do recommend that pretty much any time you're going to do a regression, you're considering looking at the data, seeing what form it takes, making sure that the linear model seems to be appropriate. So if this ever pops up, we'll be able to look at it. There we go. So when we see here is we get to see those scatter plots we had seen just a few seconds ago. And you can also see how other variables, like for example, the square footage of the house, is pretty related to the taxes. Once again, not a surprise. Look where they come together. You can see some density plots of these things, and useful or not. We can actually see the correlations, which is kind of nice. And just to give us an overview. But the first thing I'm going to do is build up a model that predicts price from square footage. So let's go ahead and do that. We know how to do this, so this will be our simple models, SLR. I'll call it simple linear regression. Is our prediction of price based on square footage. Notice that they're all capped because that's what it was, not square root, square footage. For the data set, Albuquerque home, and I can run that and look at a quick summary of my SLR. So let's pop on down to the bottom, and you see here, all right, so we got our square footage. And let's interpret what this means here. I believe it said that the price was in hundreds of dollars. So what this says for the intercept, it means if the house has 0 square feet, then I expect this to cost $4,700. So that would be about $4,700. And you might say, well, that really doesn't make sense. And honestly, you're right, because these are all for houses. There's no empty lots in this particular data set, and you can verify that by diving into it. So that intercept really doesn't have much interpretation at this point. That would be extrapolating. We don't see much of a reason to talk about that. However, the square footage term, 0.61, essentially implies that for every square foot that the house increases, for every additional square foot in the house, the price goes up by about $0.61 so about $610. That seems a little bit high. So let me go ahead and I want to verify that we're in hundreds of dollars. It does say selling price in hundreds of dollars. So this is square footage of living space. Essentially what we're seeing here in our prediction, this is, $0.61 would imply about $60. So for every additional square foot, the housing price goes up by about $61. And if you look here at the p-value, we get an extremely significant p-value, which is not a surprise. You can look at the graph, and we saw that there was a clear linear relationship, looked to be increasing. We definitely see a relationship, good predictor. I also can come down here and see the residual standard error. That basically says, plus or minus 2 standard deviations. What that's telling me is, boy, that standard error is actually pretty big. It's plus or minus $400 if I go plus or minus 200 there. So plus or minus 200, fairly, $40,000 range. If you tell me the square footage, I can get in about a $40,000 range. Is that good, bad? I don't know. That's if all I have is square footage, that's not a surprise. But I can also see my R-square about 72% or 71%. Adjusted R-square we don't look at too much in simple linear regression, but again, about 70% of the variability can be explained solely by the square footage of the house. If I want to make a quick graph of this, I'm actually going to do this as well. There's a couple things you can do in ggplot to aid you here. So if I want to Albuquerque home, I'll do a ggplot where the x is the square footage and the y is the price. Oops, sorry about that. I needed to make sure this is the AES. And we'll just do a geom point so we can at least just see the simple data set. And pretty clearly increasing. There's a way I can just simply say, hey, can you put that straight line, that best line on here for me? There's a function or another geom called geom smooth. And if you put geom smooth by itself, you're going to get this kind of weird curvy line. And actually, I do see a point out here that's causing this weird curve, but there's this outlier. Maybe I want to consider that and think about that a little bit more later. But how do I plot the straight line? That's not a straight line. That's some specialty curve. Well, I can actually say I want method equals, and then in quotes I can put LM, saying, hey, when you plot the line, put the linear model on there. Don't put that weird curve. And when you run the linear model, there's our equation of line of best fit. The blue line is that. Now, if you look also carefully, you see that gray border. That gray border, remember we talked about confidence intervals or prediction intervals more importantly. Those are giving us some ranges of the standard error of the line. That's actually a confidence interval. So the predicted, not the prediction, but it gives us a range of where we expect that line would be with different samples, somewhere within that band. And if you look closely, you'll see that it does kind of pinch in a little closer in the middle, and it spreads out on the edge. Now, I might ask one more question for you. I'm going to pull up my summary one more time. And I notice that I have my equation here. I say, I wonder, there was that weird outlier with a really big square footage. I wonder what happens if I take that out. Now, I'm not saying drop it. I'm just saying I'm curious. How would it change my results? So to do that, I'm going to use the filter function. I'm going to filter out that extreme value. So filter, I want it when the square footage is less than, we'll say 3,000. There's one big house in this case, and it's kind of messing me up here. And then I'll go ahead and say, all right, now that you have that, I'm not going to plot it actually, I'm just going to save that data set called Albuquerque Home, no outlier. And let's try a no outlier model. So I want to do the exact same thing I did before, except now I'm going to use Albuquerque Home, no outlier. And I'll look at the summary of this model. I forgot I didn't run this yet. And when I do the summary of the model, we can compare. We see the old model up here said, all right, each additional square footage gets us about $60, $61. Without the outlier, it says every additional square foot gets me about $70, $69. So it actually changed the slope. Why? Let's look back at our picture. With this outlier, it's kind of pulling the line down. Remember, we want to minimize the sum of squared residuals, and that's a really big sum of squared. So if we get rid of it, it kind of allows this to fit a more natural line. I'm not going to graph it there, but I just wanted you to be aware that outliers can have a large effect. In fact, look at our R-square. Our R-square has gone up to almost 80% just by the removal of that 1 point. So we did a lot of work here with simple linear regression, but maybe we can try some multiple regression as well. So let's do a quick multiple regression model. Come down here. Well, I'm going to go ahead and leave the outlier in for now. So the multiple regression, I'm going to go ahead and use the price, but this time I want to predict it as a function of square footage, age of the house, and we'll say the taxes. Those are the three things that I'm interested in looking at. And again, as I said, I'm going to leave the outlier in for now. I did it again. Square root instead of square footage. I guess it's just force of habit. And I did this too. Tax. I apologize for my errors there. So when I run it now and I can look at the summary, we're going to give this a look. And we'll say summary mult model. Let's take a look. Come on down to the bottom. And as we see here, square footage. Oh, square footage is significant. But what's interesting is it says, it's only worth $40, $41 for each additional square foot. What changed? Well, that's an odd thing. I'll come back to that in a second. It also says, well, age is negative. So as it gets older, it costs less money, which is not a surprise, but it's saying for every additional year it gets older, it's going to lose about $80 of value. That doesn't sound right. But actually, if you look here, you see my p-value says, you know what, age didn't really matter. We kind of saw that in the graph. It didn't seem like age was that important. So if I were to do this again, I probably wouldn't include age in the model. I'd say age of the house, that's not a useful predictor. I'm going to stick with the square footage. I can also come down here to tax and say, all right, tax says every additional amount of tax, I can expect another $53 in valuation. That's weird. It seems like as the taxes go up, I get more money. And you can say, well, wait a minute. If the taxes are going up, why would the price go up? I would think that people wouldn't want that. Well, it is significant. And you could say, well, maybe it's a reverse issue that, hey, if it costs a lot of money, it costs a lot in taxes. So it's not that an increase in taxes causes an increase in price. It's an increase in price causes an increase in taxes. But there might be some other stuff going on here as well. If I come down here to the R-square, I do see a multiple R-squared of 82%. It did go up. And I see an adjusted R-square of 82% as well. And I'd say, well, that went up. But I'd still be a little bit iffy because age just wasn't important. And I would probably drop it from my model. Now, there's one other thing that I want to look at before we end this video. I want to say, the square footage of the house, as the house gets bigger, the taxes are probably going to go up. And that means our x's might be related to each other. Remember we saw this big change in the coefficient of square footage? It went from $60 a square foot to now $41 a square foot. Maybe there's something going on with that tax variable. Maybe that collinearity thing is rearing its head. So to check that, I'm going to go ahead and find out what is the VIF of the multiplicative model. I may need to reload the car package. I do need to reload the car package. So I run the VIF, and when I come down to the bottom, lo and behold, what do I see? Well, the age looks fine, but bad news for that is that age wasn't useful at all. But my square footage and tax both have VIFs about 5.5 and 6. And it's saying, ooh, we're kind of in that caution territory, warning. These are kind of the same thing, and it's starting to cause some problems. What's the problem? Well, originally we said the square footage, an increase in 1 square foot gave us about $60 in price. Now we're saying an increase in square footage of $1 gives us only $41. It's a pretty big change. Why is that? Well, the tax is kind of pulling some of the explanatory power from square footage. And when we saw that in the GG pairs, I can actually slip back here a couple graphs, we can probably recall that there was some sort of a relationship between the price, here, I'll see if it'll open up here for me, between, not the price, the square footage and the taxes. Because of that, that's that multicollinearity thing right here. See this graph down here, square footage and taxes. And actually the square foot tax correlation is 0.85. That's huge. And that's saying, be warned, I don't recommend you put them both in. Honestly, if it were me in this situation, and you said, well, what's the best model? If it were me, I'd say the best model says, just use square footage. Nothing else. Nothing at all. Just square footage. Why? You say, well, taxes were important. They were significant. But that multicollinearity caused some problems. And it says you probably don't want to add that complexity. We will spend a lot of time, pretty much all of next week. We have basically 2 main topics. Indicator variables, how to deal with variables like this. Is it in the northeast corner or not? Or northeast part of the city or not? Or maybe even some categorical predictors. That's going to be a big part. And then also just how do you build these models? How do you make decisions to what you would say, quote unquote, the best model? So we have a lot of time to work on that in week 7. This concludes week 6, and I hope we're moving on our way in learning more and more about regression.